Welcome to Survey Matters with Duncan-Parnell. My name is Mark White. I'm the Training and Support Manager for DP. Today we're getting back to basics. This is round number 2 in our series, and we're going to talk about robotic total stations. But before we get started, please like and subscribe. So in our last video, we talked about getting back to basics with RTK, or real-time kinematic surveying, and GNSS. Today, we're going to get back to basics with the robotic total station. So what is a robotic total station, or some people will call it an RTS for short? So let's talk about first what a total station is. So a total station is a precision electronic instrument that measures angles and distances. So why total? Well, back in the day before the total station, we had what was known as a theodolite. And a theodolite would measure horizontal angles and it would measure vertical angles with the telescope. The total station added an EDM, or an electronic distance meter, that could also measure distance, and that gave you a total measurement because now we could measure angles and distances, and that's where total station comes from. So what makes it robotic? Okay, robotic total stations allow remote operation by a single user. They have motors built into them and they have radios. So with a traditional total station, you had to have one guy stand behind the instrument. He was the instrument man or the instrument operator, and he would turn the instrument manually and press a button to take a measurement. But with a robot, and then also, you had to have one guy that walked around with the rod and a reflector on it. And that is what was used for the measurement. So two-person operation. One operates the instrument, the other operates the rod. But with a robot, we have motors built inside the instrument. So once it locks on to the prism or the reflector, it can follow that around automatically, and radios to communicate that angle and distance information back to the data collector, back to the user at the other end. Okay, so it allows for a one-person operation there. So let's talk a little bit about what it's actually doing when we're surveying with a robotic total station. So the instrument, like I said earlier, is going to measure horizontal angles as I turn it from right to left in a circle. There's actually a circular angle encoder built into the base of the instrument that's split in 360 degrees. So as it turns, it's measuring angles there. There's also a vertical angle encoder built into the trunnion of the instrument, so as the telescope moves up and down, it can measure the vertical angles as well. Okay, so there's that vertical angle measurement. And then we have the EDM built in, which the EDM emits a light wave out. That light wave is pointed at a reflector called a prism, and that prism bounces the light wave back to the instrument. And since we know that it's a light wave, so it travels at the speed of light, we know the length of the waves that are being sent from the total station. We can use that information to calculate how long it takes to get to the reflector and to come back to the instrument, and we can figure out the distance from the instrument to the rod there. But one important thing to take into consideration, which oftentimes gets forgotten and turns into a support issue, is the prism constant. All right, so corner cube prisms, which are what are used in all surveying prisms. This is a 360 prism, so that as you walk with the rod, the robot can see it at all times. It can be just a regular round prism though. But surveying prisms are traditionally going to be what's called a corner cube prism, piece of glass that reflects things back. It has an offset because as that light goes into the prism, gets reflected back, it takes a little bit of time to enter and exit the prism, okay? That translates into usually a longer distance actually being measured, because it's taken a little while for light to get in the prism and come back, so it indicates the length is a little bit longer than it really is. All right, so we can correct that by using a constant and also positioning the prisms where we position it. You'll see these prisms don't line up with the center of the rod, right? But where you position these prisms can have an effect on it. And then also using a constant in your software can correct up for that time that the laser takes, or the light wave takes, to get in the prism and get back out. That constant is determined by multiplying the height of the prism by the refractive index of the glass that's being used, okay? And all prisms are going to be marked with what their constant is. You know, whoever manufactures that prism is going to come up with the constant, come up with the time it takes for that laser to get in and out, and they're going to set a constant usually marked on here. Like in this prism, it's actually on top of the prism here. If I take the glass off, it's written up there. Other prisms, it's going to be stamped somewhere on the prism, okay, so we can find that. Some of the common ones are 0. You're going to see 0 constant prisms out there, negative 17 and a half, negative 30, negative 34, and negative 40. This one actually has a positive 10 due to where the prisms are located. So you actually have to add 10 seconds, or add 10 millimeters instead of taking millimeters off of the distance there. But most of them are either going to be 0 or negative, and the most predominant ones for the round prisms that you see out there are 0 and negative 30, okay? Those are the most common ones for aftermarkets. But it's very important to know that there is a prism constant in use, and that you need to set that in your software so that your distances are correct. Now, Trimble robots they're set to 0. So back in the old days, you used to put the prism constant in the instrument so that it was kind of taken care of. Nowadays, we handle that in the software in Trimble Access. I'll show you that in the Getting Started guide we're going to do. Just know that this is set to 0, so whatever this prism constant is, we got to keep up with that in Trimble Access software. There'll be a place for that, all right? But you got to correct for your prism constant, or your distances will be off there, okay? So let's talk about how a robotic total station is measuring out there in the field. Now, when we talked about GPS, GNSS in our last Getting Started guide, or our last Back to Basics video, I should say, the satellites tell your GPS receiver where it is, and then we get corrections to tighten up that position some, right? We talked about that. A total station doesn't know where it is. All right, so an important concept with total stations to remember is you need control points, and you need 2 of them to make a total station work. And I'm about to explain why, but here I've got 2 control points up there, the triangles on the screen. I'm going to set my total station up over one of those control points, and it's got to be a known coordinate, okay? So known coordinates on these control points. So we're going to set the total station up on one of them. Then we're going to set the rod up on the other and take a measurement to it. All right. And this is what is known as a backsite in surveying terms. Set the instrument up on a known point, set the rod up on a known point, measure that. That's our backsite. And what that does is it sets a reference azimuth between the 2 known points. So all the measurements we take are then referenced to that azimuth. So all these angles that we turn are angles, horizontal angles off of that azimuth. Then we can calculate where we are though. And it also serves as a check, okay? Because if I set up on a known point and I measure to a known point, if that distance measures well, if that elevation measures well, then I know that I set my instrument up properly, chose the right points, measured the instrument height correctly, and those sort of things. So it says it serves as a purpose to set the reference azimuth and also check my setup there. So again, what we're measuring here, I've got a little picture there, the 2 control points. The black line is my backsite. You see I've turned an angle, and I've measured a horizontal angle and a vertical angle over there to the rod, which is at the red point, and measured a distance, or a slope distance, which is the red line. So we're measuring a horizontal angle with the instrument. We're measuring a vertical angle as we sight the prism, turning the telescope up and down. We're measuring a slope distance. We have to have that correct prism constant in there, right? We've got the height of the instrument, where we measure to a mark here on the side of the instrument, or a mark down here on Trimble S Series robots, to give us the height of the instrument over the known elevation of our control point. Then we have the height of the rod from the tip of the rod to the center of the prism there. And with that information, we can reduce that raw data, horizontal angle, vertical angle, slope D, heights, and we can reduce that to an azimuth, a horizontal distance, and an elevation difference between the control point the instrument's on and the shot we're taking with the rod, and we can create coordinates for all those points that we shoot with the rod. So take that rod distance, reduce it to an azimuth. Since it's related to that reference angle between two known points, we can calculate that azimuth, go that distance, calculate that elevation difference. Boom, we got a coordinate for the point on the other end. All right, so let's talk a little bit about the motors inside these Trimble S Series instruments, because they're different than anything else on the market, okay? Trimble pioneered a system called mag drive, and what that is a direct drive, frictionless electromagnetic drive technique, similar to what they use in the maglev trains, magnetic trains over in Europe, where the trains actually kind of float across the rails and don't make direct contact due to magnetic force, and that allows them to have less friction and to go very fast, be very efficient. Okay, same thing in here. We've got opposing magnets with a electric coil in between that controls how the instrument moves. So there's no gears, there's no whining like you hear on some other robots where they have geared motors in there. And that allows for really high speeds. And why this is important to you if you're using a robot, that means you can walk faster and it's going to track you and it's not going to lose you, okay? Especially when you get close to the instrument, because as you get closer to the instrument, a small movement in the rod is a big movement for the instrument, right? Because the angle gets smaller the farther away you go. So it allows you to get closer to the instrument and be able to move at natural speeds and not lose lock. Allows you to be a lot more productive there. And then also there's an angle sensor that's integrated into that servo drive, and that allows for some really nice automatic corrections with these robots and give you increased accuracy. So if you've ever used a total station and clamped the horizontal clamp down on a set angle and then turn the scope up to look up the side of a building or something, you'll see even though that horizontal tangent is clamped and so it won't move side to side, as I turn this up, your horizontal angle will drift. Okay, that's just the way total stations work. But since there's an angle sensor aligned with the servo drive can correct for that out of plumbness, if you will, and it will keep you on a plumb line, so that's going to keep your accuracy up. It'll also correct for collimation errors from one face to the next as the scope flops for more accurate measurements. And if the instrument's tilting in the trunnion side to side, it will correct up for that trunnion axis tilt. And that leads us to another technology that's built into these called sharpen, which is also unique to Trimble. That allows the instrument to remain locked at a target. So once the instrument is aimed and it stops moving, the servo gets placed into holding mode where it's literally locked on that angle. Okay, and I can tap it and it's not going to move. Now, if I grab it and move it, it'll break that holding mode and it'll move. But if I just tap it or anything, it's locked on, it's held onto that. And what that does is it makes fine adjustments. So if it starts going out of level during the day a little bit, maybe you set it up and it was frosty in the morning and now it's thawing out and the instrument's getting a little bit out of level, that servo is going to make some fine adjustments to it to keep it on that backside line. Also, if it were to get bumped or something like that, slight bumps, it's going to take care of that as well. Again, increasing your accuracy as you work robotically. So let's look at some of the different robots that Trimble offers. This is the Trimble S5. It's what I kind of call the workhorse of the robotic fleet here. Comes in 1, 2, 3, and 5 second accuracy. It has that sure point built in, it has mag drive built in, and it has something called DR Plus, which is our direct reflex plus. Direct reflex is just our reflectorless technology, okay? So it allows you to measure points without having to have a prism. Aim it at a tree, you can take a shot, aim it at a building corner, take a shot without having to put a reflector or a prism on it, okay? And then the next one in the fleet, is the Trimble S7. It comes in 1, 2, 3, and 5 second accuracy as well. Has the same sure point, has the mag drive, has the DR Plus. But what it adds in is something called Trimble Vision. And that's where in this little spot right below the lens there, it puts a camera. So now you kind of have the best of both worlds. You're running the instrument from the rod, but you've got a camera, so it's like you're the instrument operator too, looking through the scope of the instrument. So you always know where everything is. You can take reflectorless shots without having to come over and look through the telescope. So it really does give you the best of both worlds there. They also add some technology into the S7 called SureScan. It's not a full-size scanner by any means, but it allows you to set an area and take reflective measurements up to 15 shots per second to do something like a stockpile or anything like that, where you're not going to get the detail you get from an X9 or even an SX12 that we'll talk about later, to do building point clouds and things like that. But if you're just trying to get quantities, areas, lay of the land, things like that, you can use SureScan to automate some of that as well. All right. The next robot in the series is the Trimble S9, and this is really our offering for monitoring applications and higher end accuracy. You'll see it only comes in 1/2 second accuracy and 1 second accuracy. It has SurePoint mag drive. It has high precision DR, which is a shorter range but greater accuracy for reflective shots. Again, if you're doing monitoring, things like that. Also has something called long range fine lock. And what that does is it reduces the size of the laser that's being emitted to lock onto the prisms. Like, the farther a laser gets away from the instrument, the larger it's going to be, right? You get out to 1,000 feet, it's going to diverge and be larger than it is at the instrument. And if you're in a monitoring situation where you have multiple prisms that may be close to one another, what fine lock allows you to do is lock on the correct prism, because it really dials down that beam at a farther range and gives you that ability to lock on the correct prism at a longer range. It can come with Trimble Vision as well, and certain models you can get SureScan in with the S9 as well. Now, the last robotic total station offering from Trimble is the Trimble SX12, and this is our scanning total station, okay? Only comes in 1 second accuracy, high accuracy instrument, has that SurePoint, has the mag drive. Now, the Trimble Vision built into this thing is a little more special because it's got multiple cameras on it, up to 8.1 megapixels in each camera. It gives you a 107 times zoom on the telecamera. So that really allows you to zoom in on objects that are way far away, 1,000 foot plus, and actually see detail on them. And then 0.69 millimeter pixel size at 50 millimeters, at 50 meters. So that gives you the ability to get good quality, high quality pictures that you can use back in the office for total station photogrammetry and Trimble Business Center. Okay, so a lot of vision technology built into the SX12. And then it's our full-fledged scanner as well. So 26,600 points per second. Now, that's not the 500,000 or 1 million of an X9 or, a high-end scanner like that. But for civil applications, intersections, roadways, bridges, site surveys, things like that, 26,600 points a second is going to give you plenty of information to get a very accurate point cloud to do surveying back in the office out of that point cloud. Now, some of the data collectors that you can use to run these robots, the first one is one probably not a lot of people know about that works with the S5, S7, and S9, but that's the TCU5, okay? And that can actually be fitted on board here on the back of the robot. So if you're in a situation where you're not going to use it fully as a one-man crew, but maybe you're going to use 2 guys at the robot and you want that onboard data collection solution, you can get a TCU5, hook it on the back, and then it also has a robotic holder that you can use to put on the rod as well. That does not work with the SX12, just the S5, S7, and S9. And then the main data collectors that we sell, the TSC5 there, it has a 5-inch screen running Android as the operating system. It'll run all the robots plus the SX12. All of these will run all the robots in the SX12. The TSC7 7-inch screen, 5 and the 7 have the full keypad on them as well. The 7 with the 7-inch screen is running Windows 10 on that. The T7 is a 7-inch tablet that's running Windows 10. And then the T10 up there, that's our 10-inch screen, and it will run Windows 11 on there as well. So all of these can work with robotic total stations. They all have radios that mount on the back and allow for that connection to the robot, or to run the SX12 scanner as well, just depending on the size and whether or not you want a keyboard, okay? So let's wrap up a little bit. Talking a little bit about total stations, what they are, how they work. Robotic total stations, what sets them apart from regular total stations, allowing you to work one man very accurately. You know, don't forget, when you're using a total station, it's not like GPS. Just go out there and it'll tell you where you are. You have to have known coordinates to get started. So if you're new to robotic total stations, that's a question I get every now and then, or I see people whose data is a little jumbled up because they didn't know they needed known coordinates for that, all right? So then we talked about some of the different Trimble RTS models and the different data collector options. Now, just like with the Getting Back to Basics for RTK, we're going to come out with a getting started guide for robots as well. So be sure to subscribe, and when you subscribe, activate those notifications so you know when we drop that getting started guide, all right? So hey, thanks for tuning in to this edition of Survey Matters. I'll see you on the next one.